Have you ever wondered how the production rate, the time a product spends on the assembly line, and the number of products produced related? Let's take a close look at Little's Law and try to understand this very common as well as very important aspects of industrial operations in detail. In this short video, we will first understand what Little's Law states and under what assumptions it is valid. Then we find the variables and formulate the equations. And then comes the most important part, the real-life applications of Little's Law. Little's Law states that under steady-state conditions, the average number of items in the system equals the product of average rate at which the items arrive and average time an item spends in the system. So there are three variables, namely number of items in the system, rate at which the items arrive, and the time an item spends in the system. Let's take a look at them one by one. Work in progress, abbreviated as WIP, is nothing but the formal term given to the number of entities in the observed system. In case of small industries, it can be easily obtained by manual counting, but in case of large companies, when this option is not feasible, we can get WIP from the ERP data, which means Enterprise Resource Planning data. Consider the example of a supermarket. For this supermarket, the WIP would be the number of people in the checkout queue. The second variable is throughput, which is basically the rate at which the items are produced. We measure this by counting the number of parts produced in a known period of time. Let us take the same example of the supermarket for our ease of understanding. The throughput in this case would be the number of customers per hour. Our final variable is the time a product spends in the system. This is also known as the cycle time or lead time. Generally, we do not measure this cycle time for every product. Instead, we use the average cycle time because this is of more importance to us. In our same supermarket example, the cycle time would be the time elapsed between joining the queue and leaving the supermarket. The law clearly mentions under steady state conditions. So what does steady state conditions mean? It means that the rate at which the items arrive in the system is equal to the rate at which the items leave the system. Also, all products should exit the system eventually. Nothing stays in after its completion. The system should be stable without any major fluctuations in arrival rate and throughput. And of course, to use the equation, consistency of units should be maintained. Little's law can be considered to be analogous to the water tank situation. Observe this figure and use the basic principles of flow. What do we notice? The quantity of the water in the tank is equal to the rate of outflow or inflow multiplied by the average time a water molecule spends in the tank. We write the Little's law equation as L is equal to lambda times W, where L is the average number of items in a queuing system, lambda is the average arrival rate, and W is the average waiting time. Now we will see how to apply our newly learned theory in some real-life scenario. Before we go ahead, let's define one more term which is commonly used, turnover ratio. It is the reciprocal of work in progress. We have been given a scenario. A fast food restaurant processes on the average 5,000 kgs of hamburger per week. The observed inventory level of raw meat over a long period of time averages 2,500 kgs. The rate lambda is given to us as 5,000 kg per week, and 2,500 kg is the average number of items in our queuing system, which is L. Lambda and L being known, we can calculate the turnover ratio, which is lambda by L, and it comes out to be 2 times per week. Now we will see how to apply this principle in service management. A restaurant processes on average 1,500 customers per day in 15 hours. On average, there are 50 customers waiting to place an order, waiting for an order to arrive or eating. A thought to ponder upon: does the duration of shift matter to us? Yes, it does. because we are concerned about the rate per hour, not the rate per day. So our lambda is 1500 customers per day, which is divided by 15 hours per day and gives the lambda as 100 customers per hour. L, which is the number of items in the queue, is given as 50. To find how much average time a customer spends in the queue, we simply use W is equal to L by lambda and get the waiting time as half an hour. Another application of Little's law is workforce management. A certain Japanese company has 36,000 employees with 7,200 women. The average term of employment for a woman is 37 months, whereas for men it is 200 months. L woman is directly given as 7,200. We can find L men as total employees minus women, which is 28,800. The variable W in this example will be the term of employment. Thus, W men is equal to 200 and W woman is 37. The arrival rate will be calculated as L divided by W, which is 194.6 employees per month for women and 144 employees per month for men. To get the annual rate, we add them up and multiply by 12 to get 339 employees per year. Let's analyze an assembly line scenario. Watches are produced by an assembly line consisting of 20 workers. The line produces 4 watches per minute. We can see here that the rate is 4 watches per minute and L is 20. Hence, W is L by lambda, which is 5 minutes. We can also find out time taken to assemble one watch. It is simply reciprocal of the frequency, which is 0.25 minutes or 15 seconds. Wondering how we can use Little's law for cash flows? Here's how. A company sells $300 million worth of finished goods per year. The average amount of accounts receivable is $45 million. It can be easily inferred that the rate of arrival lambda is $300 million per year and L is $45 million. Hence, the time taken to receive the payment after billing is done, which is W, is calculated as L by lambda and is found to be 0.15 years. On multiplying by 12, we get 1.8 months. This graph shows the relationship between throughput and inventory as stated by Little's law for different values of waiting time. As L equal to lambda W, the plot is linear and the slope of these lines represents the reciprocal of waiting time. Now, it's the time to summarize the key takeaways from this video. As you might have noticed, Little's law is quite simple, but its applications are vast. The law is a robust tool even in case of some fluctuations because the calculations are supposed to be done with average values of all quantities. And from the graph that we looked at a few seconds earlier, we can conclude that increasing the flow rate and decreasing inventory both have the same effect on productivity. If you have any questions, feel free to ask them in the comments.